Okay, so in this session, I'm going to derive quantum search algorithm, also called Grover's algorithm, using quantum simulation or Hamiltonian simulation. So we will see that we can think about Grover simulation from a different perspective, and that will not only help us redrive uh, Grover's algorithm, but we will also see that we can come to a deterministic quantum search algorithm. Grover's algorithm, as you remember, was a probabilistic search algorithm that after an R number of iterations, we are closer to the solution, but we are not guaranteed to be right exactly at the solution. So there's always, a small error probability. That's part of the algorithm. But the way we will drive it today, we will have a general search algorithm that can also be used to set up a deterministic quantum search algorithm. Of course, there are errors from other ways that will come up because of quantum computers being noisy, but the algorithm itself, in principle gives us a way to have a less noisy output, or an algorithm with this with no error in its solution. And the method that we will use for this will actually also illuminate the way quantum algorithms can perhaps be designed, because so far we have only discussed how to analyze an algorithm. We didn't talk at all about how to design a new algorithm to do something that you want to do, and you want to think of a way to do that. So this re-derivation of Grover's algorithm will also give you a way of deriving algorithm from a different perspective, and hopefully you can perhaps use it to derive or design new algorithms of your own. So that's why this is lecture important in this sense. Okay, so let me begin by sharing my screen. Okay, so today we will discuss quantum search algorithm again, but we will derive it as quantum simulation. And we'll also get to know what we actually mean from quantum simulation. I understand that many of you, do not have a physics background. So a couple of things, might not be very clear to you, but that's okay. I think overall scheme is something that I hope that you will all be able to get. So the idea is this, that if you remember Grover, algorithm, that we have a certain search space. So this is, the space that contains everything that is solution and also everything that is not solution. So and we divided it into two axes, if you remember, a perpendicular and an axis parallel to the solution. And we say that suppose we start from some state psi. So we called it S back then, but let's call it some state psi. So this is some state, and you can imagine that our algorithm has to be in such thing that we input that algorithm to it, and the output ideally is omega. That's what we actually want. So we want to evolve the state of our quantum system from whatever the starting state is towards the state that we desire, and we desire the state to be a state that is along the solution. So that's what we want. So we want to evolve our quantum system in in the direction of the desired state. And that desired state for for Grover algorithm is the solution to the search problem. So let's say with this logic, can we come up with the algorithm that will do that? And while we do this, let me also introduce the concept of Hamiltonian. So Hamiltonian, for beginners, you can think of it as an operator that depends on the kinetic and the potential energy of the system. So it's an operator that depends on the kinetic and potential energy of the system. So this is also sometimes called the total energy operator. And we can completely specify a problem through its Hamiltonian. For example, we have a quantum system which is in some state psi 0, and if we want to see what the state of system is after some time psi of t, it's given by this unitary evolution. So this is unitary operator. This Hamiltonian is not a unitary operator, but whenever this is a Hermitian operator. So whenever we put any Hermitian operator to the exponential, this becomes a unitary, because then this operator has all the eigenvectors, eigenvalues as with unit magnitude. So this is a unitary operator, but this can evolve any quantum state psi under this Hamiltonian. So it's, if you want to picture, what I'm talking about, you can imagine like this. For example, you throw a ball, and if you can prescribe its initial condition, like what are its velocity, momentum, etc., and you specify what are the forces that are going to act if there is any rocket attached to this ball, which is giving it some force continuously in a particular direction, or maybe there is some rotator, and then you specify the environment through potential energy terms. With this potential energy and with this any forcing function available on it, you can evolve the initial state to a final state, and you can predict what would happen. And if you can physically set the system in the same way, that's what it would happen. You set your system with some initial coordinate, and you prescribe the forcing function and potential energy, and if you are able to exactly simulate that, your system will evolve from the initial state to this final state. So this is in Newtonian physics. So quantum mechanically, we can equivalently think like this, that this psi is our initial state, and then if we can come up with a Hamiltonian under which the evolution will take us to a state that we want our system to be, if we want to solve some problem. If we have any Hamiltonian that is there, of course this will evolve, but this will evolve to some state. And if we want to use this to solve a particular problem, then we will have to engineer this Hamiltonian to make sure that the system evolves to something that we desire. And since we are sort of simulating a quantum mechanical system with this is also called a quantum simulation or Hamiltonian simulation. And the algorithm design essentially boils down to finding this operator, which essentially depends on Hamiltonian. So basically what we are saying that if we can find a Hamiltonian plus this time t for which we have to simulate. So this time t and this Hamiltonian, they both can be combined to tell us where the system will go from state psi to state psi of t. And this is what this is a scheme that we will be using now to design the search algorithm. Okay, any question or confusion about quantum evolution? Perfect. So in general, when we have a physical system, it's a non-trivial task to write its Hamiltonian. So we are not going to, be going this route that we will describe a physical system and then try to formulate its Hamiltonian. We will actually do the reverse. We will try to write the Hamiltonian that we think can solve our problem, and then we will convert that Hamiltonian, to a form that can be simulated on a quantum computer, and then that physical part, that how the Hamiltonian that we specify uh, using some symbols can be translated into the physical system. That is actually what is being done by the quantum computer anyway. That whatever symbols we use to specify certain evolution of the qubits, when we send those instructions to the module that translates instruction to the hardware level, actions, that's how actually it prepares it, sort of enforce the, if you think about in terms of this ball moving through atmosphere, if we specify initial condition, we specify potential energy, kinetic energy, sources, etc., and then we give it to a quantum computer, and the quantum computer essentially prepares this potential energy field and these forcing functions, and then starts this system initial condition and let it evolve. And after a certain time t, it measures its state. And that's what we are going to do. We are going to think about a Hamiltonian and find the time t that is required to simulate, and then we will develop an algorithm that can be translated to the hardware language. Okay, so let's start with the Hamiltonian specification. So we can, guess one thing. By the way, this exponential can always be expanded using this exponential. So if you remember, this exponential x is 1 plus x squared over 2 plus x cubed over 3 factorial plus x4 over 4 factorial and so on. So essentially, when we expand it, these are a lot of Hamiltonians plus identity. So in the same way, the operator can also be transformed like this. And like that. So when we have to think about this exponential operator, we still have to think in terms of this single Hamiltonian operator, because all these terms are essentially, so this is one Hamiltonian, these are Hamiltonian. The next term is Hamiltonian cube. So all these Hamiltonian operator. So let's now think about this single operator Hamiltonian, that how it should be. And for that, we see from here that we want an operator that takes us from psi to omega. So there are a couple of simple choices, but let's begin with perhaps the simplest one. So one choice is that if I have my Hamiltonian like this, I can translate my state psi towards omega. Okay, and this is my claim. And let me see how I can say this. And that is that let's try to apply this minus iota ht over state psi and see what we get. So if I apply this exponential minus iota ht, and I assume that t is small, the t is very, very small. I'm going to evolve very briefly this system, the system at state psi. So it means if the t is small, I can approximate this operator as I minus iota ht. I can ignore the higher order term, because if t is small, t square is going to be extremely small, and the contribution of the remaining terms is going to be negligible. So it means I can approximate this, and this is equal to I minus iota t omega minus iota t psi. So let's now operate this operator on psi. So I into psi is just psi. Omega into psi is let me call this number some alpha because this is just a scalar number. And then the psi into psi is 1. I'm assuming that my state psi is normalized, so psi into psi is 1. So now I can combine this psi and this psi. So 1 minus iota t psi, and let's call it some alpha minus iota alpha t omega. And we can now clearly see that evolution under this Hamiltonian by a small time t has given us some benefit, that our state has rotated from psi towards omega by a little bit. So there's no an additional component along omega with amplitude iota alpha t. So it means that this operator that we have chosen, when a system evolves under this for a small time t, it does move towards the state omega that we want. So it means our choice is good. We need to now work more on it and see its action for a general t, not only for small t, but for a general t, and also find out what is the value of t that is required to go exactly along omega. I cannot, use this one because this is only applicable for small t. And also I need exponential iota ht psi for general t. So once we have this one, I work out this function for a general t. From that, I will be easily able to find a value of t that will give me an answer that only have omega and either doesn't have psi or only a little bit of psi. So that's what my goal is going to be in the rest of this session. Is that okay? Perfect. So
Yes, sir.
let's now move back and start analyzing and finding this for general t, and then we will find t. So it's going to be a little bit, computationally involved, that I'll have several, derivations, but you need to keep this goal in mind. That's why I wrote it here, that I'm now going to work out this thing for general t, like a simplified version. And then from that, I will try to find value of t that can tell me, okay, what t should I choose for this system to evolve to a state that only have omega and either doesn't have psi or very little of psi. Okay, so let's begin by first imagining this psi to have this decomposition. Suppose I have a part along solution and a part perpendicular to the solution, where this alpha square plus beta square is 1. More precisely, it's alpha mod square, beta mod square, but let's not worry too much about that. So this is something that we have to keep in mind. And we can actually, by the way, always make this alpha beta to be real if I can take its phase part and assume that that phase part is part of this. And if I take phase part of this and assume that that phase part is this, then I don't even have to worry about these alpha beta being complex. I can restrict them to be real number. And for this analysis, let's imagine that alpha beta are real, even though you can easily do the same analysis for complex alpha beta. Okay, so, and by the way, from here you can quickly see that if I take its inner product with omega, I should get alpha, because when omega comes from left, omega 1, so alpha, omega perpendicular is 0, so this term is gone. Similarly, inner product with omega perpendicular of psi is beta. So these are the things that we might need later on. Okay, so let's now work out what the Hamiltonian is. So Hamiltonian is omega plus psi. And let me put the description for psi that we just, the expansion for psi that we just worked out. So psi was alpha omega, beta omega perpendicular, alpha omega bre plus beta omega perpendicular. So this will give us omega into omega with alpha square. Alpha into beta with omega, omega perpendicular. Beta into alpha is again alpha, beta, omega perpendicular, omega. And then the last term is beta square omega perpendicular, omega perpendicular. Which means that if I write it in matrix form, this Hamiltonian, where this term is for omega omega, I get 1 plus alpha square. And for omega perpendicular omega, I get beta square. So this is beta square come here. And then omega omega perpendicular is alpha beta. And then omega perpendicular omega is alpha beta again. So this is what I get in a matrix form in the basis omega omega perpendicular. So in this basis, this the matrix form of Hamiltonian is this. And I can also write, for this beta square, 1 minus alpha square, because alpha square plus beta square is 1. So this is 1 minus. So I can now separate it out and separate out this identity part here. And then I will have alpha square, alpha beta minus alpha square. And I can take alpha common from this. So this is identity. So if I take alpha common, I get alpha beta, beta minus alpha, alpha beta minus alpha. And if I divide this matrix also into two parts, so in the first part I take alpha common 1 0 0 minus 1. In the second we take beta common 0 1 1 0. So this can help us. This is nothing but the poly Z matrix. So this is alpha Z, and this is nothing but poly X. So first of all, we see that by rearranging our Hamiltonian, I have now been able to describe Hamiltonian operator in terms of identity operator and poly Z operator and poly X operator. And we already know how to apply this X and Z gate, and identity is doing nothing. So I have been able to express my Hamiltonian in terms of the gates that we already are able to use in our quantum computer. But anyway, this is just the description of the Hamiltonian again. But I actually have to work this thing, which let me write back. So we were trying to work this thing out for general T. And then let's try to do that now. So I can write it now exponential minus iota I plus alpha Z plus beta X into T psi. So this first term exponential minus iota IT. So this is identity. So I don't even have to write it because whatever it operates on, it will give the same thing. So this is separated out, and the rest is minus iota alpha T, alpha Z plus beta X, and psi. And let's now try to work this thing out. This is, by the way, global phase. It's not going to impact anything, so we can drop it anytime. Actually, let's drop it right now. This will make our life a little bit easier. So this is equal to just this term. And let me expand this as identity minus iota alpha t alpha z plus beta x. Then its square. Square would be minus minus square plus iota square is minus alpha square t square alpha z plus beta x square. And then there's a 2 here. Then cube. So cube is minus cube is minus. Iota cube is iota square into iota, and iota square into minus is plus. So this is plus iota alpha cube t cube 3 and then alpha z plus beta x cube, and this is how it will continue operated on psi. And let's try to work out this square term. So alpha z plus beta x square. You can't just open it with the formula of a plus b whole square, okay? Because these are operators, and in general they don't commute. That ab is not equal to ba, so I can't use a plus b whole square is equal to a square plus b square plus 2ab. This is not allowed. The reason is this, that this is only allowed if ab is equal to ba, but in general operators don't commute. So be careful when you are working with operator. So this is alpha z plus beta x, alpha z plus beta x. So alpha square z square and alpha beta zx plus alpha beta xz plus beta square z square. And we are in little bit of luck because z square is identity. So this is simply alpha square. And here I can take alpha beta common and zx plus xz. And this z square is also identity. So this is, sorry, x square. So x square is also identity. So this is beta square. Now let's see this. You can work it out through the matrix multiplication, and you will see that zx is actually equal to minus xz, which means that the sum is 0. So I'm just left with alpha square plus beta square, but alpha square plus beta square is already 1. So this term, fortunately, is just 1. Similarly, let's see what this term is, alpha z plus beta x cube. So alpha z plus beta x cube can be written as alpha z plus beta x into alpha z plus beta x square. But this is 1, we just saw. So this is just equal to alpha z plus beta x. So this term is just this alpha z plus beta x. And similarly, you can see the next term will have alpha z plus beta x power 4, and that would be 1. The following term would be alpha z plus beta x power 5, and it would be just alpha z plus beta x. So it means I can now group these terms into 2 groups. So one group is without alpha z beta x, and the other group is with alpha z beta x. So let's combine all of them. So exponential minus iota ht up to a global phase factor is identity minus alpha square t square. So this is this term, and then the next term would be actually, I think it should be alpha 4 t4, and the terms that contain alpha z plus beta x, let me take this thing common. So let's also take this minus iota common. So if I take minus iota alpha z beta x common, this term is alpha t. And if I take minus alpha common from minus iota common here, so this will be a minus iota here. So I will have, so this second term would be minus iota alpha z plus beta x alpha t minus side. And this thing is nothing but cosine of alpha t. And this thing is nothing but sine of alpha t into alpha z plus beta x. Perfect. So any questions so far or confusion? No. So let's see one thing. Let me work out what this operator operating on psi gives. So this alpha z plus beta x and psi. Let's try to find this. And for that, we can, note one thing very easily, that this is nothing but Hamiltonian minus identity. Because if you go back here, you see that this alpha z plus beta x is equal to into alpha plus I is Hamiltonian. So if I take this I here and divide by alpha, so h minus I over alpha will give me alpha z plus beta x. So this alpha z plus beta x is 1 over alpha h minus I. So it means that alpha z plus beta x operating on psi is 1 over alpha on psi. And this Hamiltonian was omega plus psi minus I. So when this omega is inner product with the psi, I get omega into alpha, because omega into psi is alpha. When this psi is inner product with psi, I get 1, so psi. And when this identity multiplies with psi, we get psi. So these two cancel. Alpha cancel with alpha, and I get omega. So this into this is just omega. So this thing now simply becomes exponential minus iota ht on psi is cosine alpha t psi minus iota sine alpha t omega. And now we can clearly see the action of this unitary operator through this Hamiltonian that we selected is to rotate our state psi towards omega as time passes. So you can see, as t increases at t is equal to 0, we have psi, because this sine alpha t is 0 and cosine alpha t is 1. But as t increases, our state goes from psi, and this component omega starts to come in. And since it's periodic, after some time t, this will actually become completely omega, but then after that it will start to converge to psi again as well. So if I draw it in this plane, so this was psi. So this, after time t, this psi has been rotated by this angle alpha t, because this makes angle alpha t with psi, and there's no a component along omega as well. And if we can see easily, if we can set alpha t is equal to pi by 2, which means that if I evolve this system or simulate this system for time t is equal to pi over 2 alpha, this exponential minus iota ht psi will actually be just minus iota omega. Because this is 1 and this is 0. So now we have seen two things. Number one, that if we can somehow simulate our quantum system under this Hamiltonian for time t is equal to pi over 2 alpha, we can see that our system will go from psi to state omega. And number two, we now have the explicit, expression for this state at any time t. Okay, so the next question is, so any question or confusion so far, or question about derivation? Okay, so far this alpha remains unknown and beta, because we defined our state psi to be alpha omega plus beta this, but let's see if we can choose this alpha, because this alpha depends on this state, initial state psi. But on a quantum computer, we can choose this alpha ourselves. We can prepare this state psi in a certain way. For example, if I start from the 0 state and apply a Hedda mod on it, we see that we can get a state which is sum over x and all combination of x states. So it means that I can now divide this superposition state into two parts. So one part is where x is not equal to w, and the other part is where we have state w. So it means that if I normalize this state now, because this has n minus 1 entries, so I multiply with n minus 1 here and divide by n minus 1 here. I can prepare two normalized states. So this is my omega perpendicular and this is omega. So it means this is my alpha. So alpha is 1 over n square root and beta is n minus 1 over n square root. So it means that instead of defining the simulation time t in terms of some alpha, I can now define it in terms of 1 over n square root. So this is pi n square root over 2. So I need to simulate proportional to the square root of the number of solutions, number of entries n in the subspace. Okay, so it's a little bit messy. So it means that t is pi over 2 1 over n square root. So now my simulation time is just in terms of the bits, because this capital N is 2 power number of bits. Okay, so now we have only one thing left, and that is how to simulate H. And for that, it's a complete discipline and a course right now, how to simulate a given Hamiltonian. I'm just, going to give a very simplistic and, a very small part of it. And that is applicable when we can divide our Hamiltonian into component parts that we can add to make up a big Hamiltonian. And that's what we can do right now, because the Hamiltonian that we defined was like this. Psi, psi. So we can say that this is H1, this is H0 term, and so on. So it means that simulating iota Hamiltonian T is equivalent to simulating iota H1 plus H0 T. However, and unfortunately, in general, this is not true unless your Hamiltonian, the components commute with each other, which means that H1 H0 is equal to H0 H1. If this is not true, and in general it's not true, then we can't write it this. So on the other hand, equivalently, I can say that this comes with some error. If I approximate this, exponential iota ht, this comes and write it as a product, this comes with error. So there are several ways to reduce this error. There are different, tricks that we can use, and there are different orders of approximation. All these calls are called trotterizations or trotter schemes for decomposing a Hamiltonian into these product terms. So this and this term. But for now, we will use this one, and keeping in mind that there is some error present. And generally, this error is proportional to the simulation time t. So if we keep this simulation time t small, we can keep the error small as well. Okay, perfect. So in general, now we wanted to simulate this exponential iota ht, and there are two things that we have to do. The first thing is that we simulate this Hamiltonian in small chunks. Let me write it like this. So suppose some index, j, which goes from 1 to r, that when I have to simulate for some time t, so instead of simulating for the whole time t, I simulate it in smaller chunks of times. So I simulate this for time delta t, simulate this for time delta t, simulate this for time delta t, and so on. There's going to be a cumulative error as well, but using this small time interval, we can keep those errors small, because this error is proportional to this small time interval error. So it means this r that we choose is the total simulation time divided by the interval that we choose. So now, instead of simulating this in full time t in one go, we simulate it in chunks of time delta t. And because of this smaller chunks, we can now divide it into these two parts. So this means that instead of this, I have to simulate it r times, and I can now simulate iota h1 delta t. So there's a minus sign, sorry, minus iota h0 delta t. And let's now work out, what these two terms of Hamiltonians are. So let's see the first one. Minus iota h0 delta t, which is exponential minus iota delta t psi psi. And we can try to work out this term, in terms of general delta t, but we can recover Grover algorithm quickly if we make our delta t equal to pi. Because if this delta t term is pi, we can see that this actually works out nicely to this minus iota pi psi psi, and then the square term minus pi square over 2, and then the square of this. The square of this is actually this itself. You can easily see, because its square is writing it twice. So this is 1. So I'm again left with psi psi. The next term is the cube term minus, and again cube gives this psi back. The next term is power 4. So minus power 4 is plus 1, iota power 4 is plus 1. So plus pi 4 factorial psi and so on. Okay, so this is I, and I can combine two types of terms. So the first is, so this is common in every term. So there's one group of terms of odd powers of pi. So minus iota pi minus pi cube over 3 and so on. And then the second part is this term. So this is minus pi square over 2 plus pi 4 over 4 factorial and so on. Now this thing is 0 because this is a series for sine pi, and sine pi is 0, and this is something that if I subtract a 1 and then add another 1, so this becomes pi square over 2 factorial pi 4 factorial. So this is a series for cosine pi, is it? Or yes, so this is a series for cosine pi because cosine pi is 1 minus x square plus x4 and so on. So this cosine pi is -1. So -1 and -1 is -2. So this becomes I minus 2 psi. So this first term, simulation time pi h naught and psi is just I minus 2 psi psi. Similarly, you can show in exactly the same way. So this is minus sign, minus iota pi h1 psi is actually I minus. So this is actually just the operator, not this part. This is minus 2 omega omega. And now you can see that this is exactly the algorithm that was the Grover algorithm. The only difference is last time we were calling this state psi the S state. So we had one box which we were calling diffuser, and if you remember, the diffuser with Hamiltonian I minus twice 0 0 into Hamiltonian into Hadamard, this was equal to this I minus 2 SS, and the Grover oracle was nothing but I minus 2 omega omega. So it means the quantum simulation is also telling us that start from a state S, which we actually get by Hadamard transform, and then you apply one oracle, let's say this Grover oracle, and simulate under this Hamiltonian for time pi, which is equivalent to this, and then you apply the diffuser or the other oracle I minus 2 S, and then do this R times, and then your state will reach closer to omega. Okay. So we are able to see that we can derive the Grover's algorithm from using the concepts of quantum Hamiltonian simulation by requiring our Hamiltonian to take our state from some state S to the desired state W. And we were able to see that if we choose this simulation time for one particular value, we can recover Grover algorithm. And for other values of pi, we have this general Hamiltonian simulation problem that we can even get exact solution if we simulate for exactly time t is equal to n square root pi over 2. Any questions? Okay, so I see there's something in chat. Okay, so if not, let's take a 10-minute break, and then we will have the question answer session.